these sort of what seemed a couple years ago like totally theoretical techniques that you would never see used in a real system are actually getting used in production at a very large scale. So thanks so much for coming up to give the talk.
Of course, thank you. I think you can hear me? Cool, great. Hi all, I'm Rehan. I lead the machine learning security engineering group at Apple. I'm going to be giving a talk about how we are using HE and how we've built systems for HE in a combination with other privacy-preserving tech at Apple to power various features, shipping across 1 billion Apple devices. So to begin with, why do we need this? There are a bunch of on-device experiences that can be enriched with information that's sitting on a server. And across all these features, we start by considering what user data would need to potentially leave the device, how privacy sensitive is that user data, and then how can we best design a system that can protect that data's privacy. This is where HE as a primitive, in combination with other tech, privacy-enhancing technologies, shines, because it provides this ability to compute unencrypted data, and that's super duper useful for information retrieval. Here's just a walkthrough of some of the features that we've shipped with HE. We introduced private live caller ID in iOS 18, and this looks up real-time caller information to identify and block spam phone numbers. We've deployed this at our own services at Apple, as well as for third parties, where third-party app developers can spin up their servers and block spam phone numbers. And they do this in a way where we're protecting the queried phone number from leaving the device without any privacy. The second system we developed was for photo search, where there are some domains that are really hard to classify with just on-device ML models, because they just require a bunch of information sitting on a server, like landmarks or places of interest, where there could be millions of these entries throughout the world. And so that's where we found a pretty good use of employing PIR as well. And finally, in mail, we provide business information for emails from United or other places that are built into Apple Maps. And again, we don't want Apple to learn which emails you're getting emails from, and so that's where we use PIR. Cool. Formally, what we want to do is we want to provide a privacy commitment that these client queries remain private from Apple, but we need to do this in a way where we can meet the practical system requirements of our billion Apple users. And what this boils down to is two, some on the client and some on the server. Okay, on the client, what we need is we need a small storage. And so there are a bunch of techniques where with big enough storage, you can provide pretty efficient protocols. But here, every feature can only consume up to a few megabytes of the storage. We want the experience to be high quality. And then on the server, what we need is, because we can get tens of thousands of queries per second, and some of these queries can be latency sensitive, we want that throughput to be fast and can be big enough and provide a communication of less than 1 megabyte, because otherwise, these features will just eat up all your data, and that's not going to be, no one's going to look upon that kindly. Okay, so to better demonstrate how we are able to achieve these goals, we're going to walk through a system we called Enhanced for Visual Search, where we were able to tag landmarks and places of interest from a global index that's maintained on the server for contents of these landmarks on your photo, and improve on-device search. Now, why we want to do this is because, let's say you've been on a holiday and you have a bunch of photos from different landmarks that you've taken on this trip, and when you would want to search for these specific sort of landmarks, before this feature, there were two ways to do this. One, you would probably just search for the city. For example, let's say I took a photo of the Chapel Bridge. I would search for Lucerne, or I would just type a generic class like a bridge or a monument. And that just was providing poor recall. And what we observed was users would get quite a number of photos. It would not be a pleasant experience. And that's where we wanted to improve this. So this is where we leverage HE And here's a screenshot of how this feature is working. On the left, where now if we type Chapel Bridge, you can see that the top ranked images are of that exact monument. Okay, and so a common question is, yes, fine, great, you built all this complicated stuff, but is it really that hard to ship something just with an on-device solution? And to show you why we needed this, we'll just start with the whole system. And so we start with this image, with this possible landmark. On device, we run this ML detector that's detecting some region of interest. And so then we just focus on this. We don't focus on the whole image. We just focus on this region of interest. We have an ML model, a different ML model that sits on device and generates something called an embedding, which is essentially just a vector of float values. And what this does is, this might be super familiar to everyone, but I'm going to go through this anyway, is it provides some semantic meaning about the original image, where closer photos are close in this embedding space, and the ones that are not as close are far away. And we can measure this with a metric called similarity, cosine similarity. Now, for this application, it's just simply enough to compute a dot product for that cosine similarity between the query embedding and all the embeddings in our database. And the embedding with the maximum similarity score wins. And that's the one that's closest. So to do this in the naive way, we could, of course, download this whole database on device. And then just run the dot product locally, select the embedding with the maximum score, and output that label. But here's sort of like, just a graph of how this storage could grow with 5 million up to 500 million. And these are very, very real numbers on the type of indexes for these kind of use cases. And so we realized that, no, we do need to send queries to the server if we are able to power these kind of experiences. So yeah, I think just parroting what I said in the last slide, where in this solution, the client queries would remain private, but we don't meet the small storage requirement, and we don't meet the high quality experience. Okay, so in an insecure setting, what this would look like is you just take the embedding, and you ship that off to the server. You compute this dot product, and you pick the maximum score, and you send the label back down to the device. And when we were talking about the privacy of this feature, we got pushback, and we said, why can't we just do this? It's an embedding. It's not the actual image. Why don't you just send this up? But what we've seen is there's a bunch of work that shows that embeddings are not private. There are very trivial reconstruction attacks that can help you reconstruct the whole image and leak all the information. So this reinforces the fact that, no, we do need to make this system private. Okay. Now recall, all we need to do is compute a dot product. And so to protect privacy, one approach is to use homomorphic encryption directly. That allows additions and multiplications on encrypted data. And so now the device is going to encrypt the query embedding under HE using a secret key that stays on the device. Sorry, compute the dot product under HE, and just ship all the encrypted scores back down to the device. And this is a perfectly valid approach. Tiptoe was the state-of-the-art approach that does this when we're shipping the system. It provides full obliviousness for this query privacy. But at the scale where we need to be shipping this feature with the throughput requirements that we have of tens of thousands of queries hitting the server, as well as the communication requirement that I mentioned early on. Yep, question?
Order of gigabytes, terabytes, exabytes?
Gigabytes, so tens of gigabytes is the order for these kind of indexes, yeah.
So is this like something that like in practice that like it suffices like for real good cases, like to offer like this like service to because you said that this was a product actually that like you launched like at Apple, so with like hundreds of gigabytes, is this like saying like a size of a database that like it can have some sort of good quality on performing these private image searches, or like do we need more? Because it feels that like this database that needs to be bigger, right?
It depends. It depends on the domain. For example, let's say all I want to do is classify popular landmarks across the world. There are millions of them, not hundreds of millions of them. I want to classify plants. There are hundreds of thousands of them. So you're right, where if I had to go classify every business in all my Apple Maps index, that's going to be hundreds of millions or billions, whatever. And that's not the position we're in right now, where we scale. And so we are not shipping at that level. Or you just pick leaking some semantically understandable level of privacy, where you would just say, OK, I'm going to leak the geohash3 index, the hash value, right? And that can sort of explain that, fine, this query is for something in California. And so sharding is an approach that we do across different features. For this specific feature, we didn't need to do that level of sharding. But yes, that's definitely something we have seen in practice.
Can you please repeat what was the biggest database size that you considered?
I can't talk about the biggest. There's some I can't talk about it. I guess is what I could say. But the order that we are thinking about using these technologies is in the gigabytes. It's not in the terabytes right now, if that helps you. OK, so yes. So what were our requirements? Our requirements were tens of thousands of queries per second and a cheaper communication per query, right? This is per query, where we want to be under 1 megabyte. So just directly applying HE did not solve this problem when we were building the solution.
So is it, would you be OK with having the server store some per client state? Or is this completely stateless protocol where the server doesn't know who the client is?
Yeah, in this case, it's stateless, but there is opportunities for maintaining some state on the server, if that can help. So I'll come later in this talk on how we send requests through oblivious HTTP. So we anonymize these requests, and so how does that play in with this server state is something that we would want to consider. But that's not out of the realm at all of an opportunity. And again, it just comes down to how do we analyze the privacy leakage here. If we can learn nothing about the query, but we understand that some user device made 10 queries today, that's a trade-off that we could potentially look at making. OK? Cool. So if we use HE directly, we maintain a privacy commitment on the client. We meet the client constraints for storage, but we don't meet our server constraints. And again, we shipped the system in 2024. There have been other PI protocols that optimize different aspects of this story. And so this is the state we were in when we shipped this. OK, so our problem is high compute and communication, because the server performs an HE operation per entry of the database. And so what we did was we combined DP with HE to solve these two problems independently. So how we do this is we design a DP-based protocol that reduces this computation while still maintaining a standard notion of privacy. And then I'll walk through some HE contributions as well and how we optimized the underlying BFV scheme that we used to reduce the communication even further. So first, let's look at DP. So how this index is organized in standard ML sort of search systems is you end up clustering data. So you never have to compute linearly over everything in the index. And so you have clusters of this, and then you have these cluster representations, which are embeddings themselves, like C1, C2, C3, C4. So what we do is we take all these clusters and we create something called a codebook, and that gets shipped down to the device. And this is relatively not as expensive. For an index of, let's say, 5 million, you could get pretty good recall with something that is in the tens of thousands of clusters. So that's a pretty good trade-off to make. OK, so we ship this codebook down to the device. And then at the time of query, the client finds the nearest cluster using these centroids that are on device and then sends that to the server. So the server responds by sending embeddings and the metadata, GPS signals or whatever for the entry back to the client. So we know that now we've reduced the server compute, right? Instead of computing on the whole index, now you're only computing on the cluster. But the server's learning this nearest cluster. And that can still potentially reveal information. For example, you could probably infer from learning cluster C2 that this query is related to bridges, right? And so you're still leaking some semantic meaning about the query itself. Okay? But we had this observation that because of the scale of our user population, many users at any given time are making queries, and we can hide this query in a batch of queries. And so what we do is we hide the clusters that we are querying for, and we provide this trade-off between efficiency and privacy, which is bounded by epsilon delta differential privacy at the user level with respect to a user's photo library. And I think I can go into details, but epsilon delta are the two parameters that control the privacy. And smaller the epsilon, better the privacy. So the intuition of how we did this is we assume two worlds, one on the left where multiple clients are making queries, and on the right where one client is not present. And in both worlds, the server's view should be the same, but it's bounded by our parameters of epsilon and delta. This system we shipped was with epsilon of 0.8, which is pretty good. And how we achieve this is we do this in 4 steps. First, the system is working in time periods called epochs. In every epoch, many honest clients make queries. Second, these clients' queries gets anonymized. As I mentioned, we route this stuff through oblivious HTTP, and so that's removing identifiable information. And so from a server's view, every query is unique. And now, even though the client queries are anonymized, the server can still link a query to a particular client. It can know a cluster can only be accessed by maybe one specific client, and so we need some deniability, and that's where a client starts introducing fake queries. Each user's querying a sample number of these fake queries from a negative binomial distribution, adding more queries, improves privacy, and in reality, to meet the DP sort of guarantees, we saw that the client could make additional 1 to 2 fake queries, and we could get that kind of leakage. Yes.
If you can go to the previous slide. So at the moment that you have like this oblivious HTTP kind of like service, so are you going like, what's your threat model? Are you going like from one server solution like to 2?
For the HTTP, yes. For the oblivious HTTP part, it runs on how oblivious HTTP runs, right? So you need a gateway and a relay, and so
part of the Apple's ecosystem, or
yes, this is Apple's infrastructure with working with partners, yeah.
Okay.
Okay. Yep. So we see the overhead of making queries to be about 2x more than the original query, and that's a pretty good trade-off that we can make in practice. Peter.
What is the definition of DP here? It's, usually in DP, there are n users, and you take one user and you change their data or something like that. This seems to be like a single user.
Yes, it's at the user. It's not at the data of a. It's not at the level of individual photos. It's at the level of users. If you can take one user out or not. Yeah.
But the server still knows the device that it's talking to. It still sees everything. Or is it seeing a batch of?
It's seeing a batch. Yes.
Okay,
Yes.
got it. Okay. So then, if you take one of the users in the batch and you swap their data
Yes, exactly.
arbitrarily,
Yeah.
okay, with or without that person, you get.
That's right.
So
Okay.
you need the second party, right?
I'm sorry?
So you need the second party. Otherwise, you can like pinpoint exactly the.
Yes, you need. That's why we ship this traffic through oblivious HTTP. Yeah.
Okay.
Yep. Okay, another avenue of leakage is query timing. And so for each query, the client is randomly selecting an epoch over which, because I think this system is something that we can deploy in this offline setting where it's not real-time search. It's tagging photos in the background. And so that's where we can leverage this, this kind of system. This would not work if you wanted real-time results for your search. And so that is a limitation. But again, for things like photos tagging, emails, these kind of things, it all happens in the background, so we're fine. Okay, so there's more proofs in the paper that we published, but essentially what this boils down to is that the server views this noisy histogram of clusters that are being queried for. It's epsilon delta differentially private in the central model, and the server is not gaining any extra advantage in this distributed model where clients are issuing queries in these random epochs. Okay, so we have reduced the computation, but the server response could still be pretty large because in this setting, you're just sending back the whole cluster. And that could be hundreds of embeddings, potentially more. And that is, again, not scalable. And so that's where we reduce the communication by leveraging HE. What we do is we go to this nearest cluster, and then for each real or fake query, this client is going to be making a sort of the cosine similarity score that I mentioned earlier under HE, right? And so the embedding's encrypted on the device. That gets sent to the server along with the cluster that we want to target. And then on the server, we're computing cosine similarity scores against all the embeddings that are in that specific cluster. And so specifically, we're using BFV as our choice of HE scheme and the RNS variant of BFV. And yeah, another thing to note is even for the fake queries, the client can just encrypt any value. So there is no leakage whether a query is real or fake. So the server then computes dot products between the query and embeddings in the cluster. And then all we return now are scores for these computations back to the client. And then the client can locally sort and pick the top K sort of results that applies to it. What we also do is we use efficient SIMD packing for BFV. And so instead of sending scores separately in ciphertext, we can merge them all in one single BFV ciphertext. And so that also helps with our communication. So we've now tried to solve for both computation and communication. A few more optimizations that we ended up implementing was the first thing is under the scheme, each ciphertext has two components. And you need this during the compute phase. But what we notice is like the message is always encoded in the higher order bits, while the noise is encoded in the lower order bits. And so to reduce the response size, what we do is first we can use a standard modulus switching technique, but we can also just sort of remove the second limb because we don't need that when we're communicating this back down to the device. And as well as we can just drop the least significant bits because that contains the noise and all of the score is in the higher order bits here. And at the end of all of this, what we did end up achieving was a 10x reduction in the server response size. Again, super significant when we're talking at scale. Okay, we also implemented other things. We used delayed modular reduction where we wait till this is absolutely needed, and we don't do this at every operation. And we also had some improvements in the eval key size, because to maintain anonymity, we cannot store eval keys on the server. Like in other HE applications, you need to send this with every request. And so again, that cannot be megabytes. And so we had to make some optimizations there as well. So finally, at the end of all of this, what we do is we get to the scale that we needed in this specific application, where you can process 25,000 queries per second. Communication per query is about 500 kilobytes. Again, the privacy guarantees here are not as strong as tiptoe. But this is a good sort of privacy model for this specific feature. And a 27x higher QPS and a 30x smaller communication was worth it. So at the end of this, what do? We meet all our goals where the client queries remain private, the client storage is small, the server is efficient, and we're able to answer queries for this whole index. All of this is out there. You can take a look at our work. We released a Swift package that is essentially the HE scheme that we use. And so it's auditable. It has all these optimizations I talked about. And we've seen a lot of feedback as well, because like I said, there are third-party apps that have also built these HE servers for certain applications. And so please have a look. The device-side crypto lives inside core crypto, which is, again, auditable and is available at developer.apple.com. OK. Yeah, I guess in summary, the main takeaway for us during the development of this, this feature was any one privacy technology might not be enough. And we have all these tools in our toolbox. And how we combine all of them to meet the requirements of the feature is essentially the journey we were on throughout this. And yeah, we combined HE with DP, with Oblivious HTTP. We also leveraged Privacy Pass for our caller ID implementation. And with that, we can service our user population and provide these features to our customers. There's a bunch of public documentation, like the Apple GitHub I mentioned. There's developer docs on how we implemented caller ID, the paper with the proofs of the search system I talked about. And there's also a blog post that sort of summarizes everything we did. And yep, that's it.
Any questions? More questions? So maybe I'll start with one. So what advice do you have for researchers, PhD students in the audience who are hoping to get their stuff into Apple products? Like what are we not doing that we should be doing, or that we are doing that we should keep doing? Yeah, what's your take on this?
I think what we've seen over the last couple of years is the best use for HE has been PIR, but not in the traditional sense of just retrieving information from databases. To power ML experiences, you just need data from different places. And the algorithms to retrieve them can be different. And so how do we make PIR more accessible to those algorithms? With the key insights of client storage is a thing. We cannot circulate the whole database down to the client to improve computation. But we are seeing a lot of we're seeing a lot of requirements for now that this technology is out there. How do we improve this? How do we scale? How do we get to those terabytes of index sizes? And maybe there's a distinction, like I said, between what a real-time use case needs versus what something that can happen in the background needs. And so one size doesn't fit all. And that's how we've been thinking about this as well. Yeah.
So you mentioned an epsilon or privacy budget of 0.8. And I was wondering if you could comment on how you arrived at 0.8, and also given that it's, I think, a finite resource, like how do you deal with that?
Yeah, so that epsilon is for how long we expect these photos processing to take over the course of, let's say, 1 year. And we understand how large people's photo libraries are. And so that's the sort of information we leverage to expect the number of queries we would get on the server, and yeah, fine-tune our parameters.
All right, if you don't have any more questions, let's thank Rehan again.